Optimizers are most important for performance of AI ML applications. AI ML applications. The optimizers are below. One is first optimizer endama gradient descent, stochastic gradient descent, mini batch gradient descent, ADA grade, five is RMS prop, ADA delta, ADAM. These are the optimizers. What is the use of optimizer, Nana? Okay. First one is again we are trying to write gradient. What is the gradient descent, Nana? The gradient descent is a simple optimization algorithm that updates the model parameters to minimize the what, Nana? Minimize what? Loss function. What is this, Nana? Underline the loss function. So delta will be written as delta minus alpha is the learning rate. This is what gradient, right? This is the loss function. Pros. What are the positive? Simple to implement, can work well with well-tuned learning rate. Well-tuned learning rate. What it means, let us take this is my curve. For this point, I am telling well-tuned learning rate. If learning rate is small, it takes long time to converge. Converge means getting the optimum value. Okay. Example in this particular thing. Okay. This is your what, Nana? This we called global minimum. Loss is close to 0. Imagine this side when I have a different learning rate, this bigger learning rate, it will be clipping, right? So that was the reason can work well with the well-tuned. What is this, Nana? Learning rate. Understood? Understood or not understood? Negative side of it, cons. It can converge slowly, especially complex models. What is this, Nana? Sensitive to the choice of the stochastic gradient in gradient descent. Model parameters gets updated at end of all iterations, whereas in stochastic model parameters gets updated by mini batches. What it mean? I have, let us say, 1 to 1000 records. In gradient descents, after all the data points, my weights get updates. Weight will update only once in gradient descent. Here in this 1 to 100, 1 to 1000, it will be split into many batches, 1 to 20 to 30, 40 to 30 to 40, and so on till 100,000. So the weight get updated batches wise. So in turn, this will have a good performance over gradient descent. Agree or not agree? Eating small by small is easy than having bunch of things. Okay, right on the stochastic gradient descent. So stochastic means for 100 records it will process. It will gather some weights. Next 100 records it will update the weights. It will update cumulatively. I will write the formula here. You will understand. The previous formula to this formula will be theta equal to theta minus alpha loss function of theta x power I, comma y power I. So this is what mini batch. Okay. Our goal is to reach here. Our goal is to what, Nana? Reach here. So that we will start. Okay. This how mini wise. It can be faster than what, Nana? Faster than gradient descent, especially for larger cell. Negatives are, it can be noisy, leads to less stability. It required more parameter tuning for stochastic gradient descent with momentum. What is this, Nana? Momentum. The momentum, it adds the momentum to the gradient term to update the rule, which helps optimizer to continue moving in the same direction, moving to the same direction, even though local gradient is small. Local momentum is set between 0 and 1. What, Nana? Momentum is set between 0 and 1. So what is the difference between this example? Will give you the brief about this. Easter regular way. Let us take, this is without, this is the point I need to reach. It will stop here. In this, did you see the difference? The momentum term pushes your optimizer to reach the minimum amount. So in this minimum, there are two things. One is local minimum and the global minimum. We have learned this somewhere in the calculus. Yes or no? Refer that. No. It will reach out to the minimum. It won't go out of that. My aim is to momentum has to, we are pushing to the same direction. So here it may jump also. It may go here also. In this without momentum. With momentum, it converges to the minimum. Okay, you got the point? Right on this. Images are more important.